Hello everyone, my name is Kieran Montgomery and I'm a third year PhD student at Imperial College London. I work with Paul Bruce and Salvador Navarro Martinez and we are looking into supersonic retro-propulsion for Mars entry, descent and landing. If we want to land people on Mars, estimates show that we need to put over 40 tons of equipment on the surface. This is far beyond the limits of supersonic parachutes, and so we need to turn to supersonic retro-propulsion. However, this field is not well understood. Questions such as what effects does the thrust coefficient have on the aerothermodynamics of the craft, or what are the flow characteristics when transitioning between different penetration modes, still need to be answered. To answer these questions, we need state-of-the-art, time-accurate computational methods. Previous studies have made use of RANS models and do not capture the important unsteady effects that SRP produces. We are using CompReal, a compressible Navier-Stokes solver written at Imperial College London. We also make use of adaptive mesh refinement to increase the resolution of the mesh closer to areas of interest. For the simulations presented, the flow is at Mach 2 at an altitude of 10 kilometers in the Martian atmosphere. In the results presented today, we vary the thrust coefficient linearly over time. This is done by increasing the ratio of jet stagnation pressure to free stream stagnation pressure at every time step. We do this with 3 different jet diameters, namely with jet diameters that are 5%, 10% and 15% of the model diameter. Here is a simulation with a jet diameter that is 5% of the body diameter. The top plot is a pressure consort log plot with the reds being the highest values and the blues being the lowest values. In this simulation, we vary the thrust coefficient over time and calculate the resulting drag and axial force on the body. The transition from long penetration mode to blunt penetration mode is captured, as well as the low pressure vortices that are shed from the jet boundaries and travel downstream interacting with the body. These vortices present themselves as oscillations in the coefficient of drag plot and could lead to unwanted vibrations for the craft using SRP as its EDL system. Here is a simulation with a jet diameter that is 10% of the body diameter. We see similar behavior for values of thrust coefficient larger than 1.4. However, for values of thrust coefficient less than 0.5, we see a steady increase in axial force since the values of drag coefficient aren't affected by the jet yet. In the poster, I include snapshots from these simulations, as well as simulations for the case with a jet whose diameter is 15% of the body diameter. I also include the corresponding graphs of axial force and drag coefficient. Thank you very much, and I welcome any questions you might have.